Next problem. A ladder 10 feet long rests against a vertical wall, as they usually do. If the bottom of the ladder slides away from the wall, the person at the top is in trouble, right? At a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is exactly 6 feet from the wall? Notice I'm putting in the word exactly. It's not in the text, but that's what they're implying. At this exact instant in time, how fast is everything changing? It really, 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 really helps to do a picture with this one. And when you do your picture, you want to think of the coordinate plane at the same time. When we deal in the coordinate plane, what quadrant do we like to work in? Oh no, quadrant 1. That's right. So if I'm going to draw a ladder leaning against the wall in quadrant 1, what would that look like? Yeah. Looks a lot like that, doesn't it? 10-foot ladder. My x distance away from the wall is positive. My y distance up the wall is positive. So I'm thinking about this being drawn on or superimposed over a coordinate plane where 0, 0 is here at the right angle. That's going to help me a lot here to think of it that way. Because if that's a right triangle, I have all kinds of tools that I can use with right triangles. Okay, what do we know? We know the ladder's 10 feet long. That's in the diagram. What else do we know? It says if the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So that means this is changing. The x value is changing. Can you put that in that fraction form? Like we had dv over dt. What's that going to be? It's not a volume. Say that again? Yeah, it's the rate x is increasing, right? So we're given that dx over dt is 1 foot per second. That value x in our coordinate plane that we've written that up as, that's getting bigger at 1 foot per second. What are they asking us to find? dy dt at a specific instant, right? So dy dt when x is exactly 6. That's what we're trying to find. So when you do these, I think it's almost, thank you, imperative is a good word. It's really critical that you identify what you know and what you're trying to find. And these pictures come in a lot. They help a lot too. Because that picture leads me to some relationships, some equations. That's a right triangle. I can think of an equation really quick that involves x and y based on that right triangle. You guys see it too? Yeah. Pythagoras. X squared plus y squared equals 100. It's really nice that there's an x and a y here, and I know something about x and I want to find something about y. That's really nice when that all fits together. We kind of reached this point on the last problem when we got to the v equals 4/3 pi r cubed, right? We're right at that point. What do we do now?
Take the derivative.
Yeah, we take the derivative because we really want to think about dx dt and dy dt, right? So, what is the derivative of of x squared in terms of time? What's 2x dx over dt, right? This is going to be 2x dx dt. What's the derivative of y squared going to be? 2y dy dt. What's the derivative of 100 going to be? 0. Don't forget that. That's where people kind of mess up a little bit, is they either leave the 100 or they turn it to a 1 or do something goofy. That's a 0.
That's not 100.
10 squared is 100. So we've got 2x dx dt plus 2y dy dt equals 0. We know one of these values, we're trying to find the other one, right? dx dt was given to us to be 1. So we can replace that with a 1. And we want to know at the exact instant when the ladder's 6 feet from the wall, that's when what is 6? X. Yeah? So here's the value, the rate dx dt becomes 1. I could go ahead and put the 6 in for x right now too. I don't know why I didn't. I just chose not to for some reason. Oh, I know why. Yeah. Yeah. And we can do that because if x is 6, we can solve for y, right, at that instant in time. So let's follow this out. dy dt is going to equal what? Negative x over y. So if I can find x and y at the instant when x is 6, I've got this done. And in fact, this little formula at the bottom, you find it for me at any instant of x, right? When x is 1, it would tell me what the rate of change of y is. So when x is 6, how do I find y? Yeah, just go back to that Pythagorean relationship. When x is 6, y is 8. So 36 plus 64 would equal 100, right? So if that happens, therefore, dy over dt is negative 6 over 8, or negative 3/4. Now, this is negative. What does that mean? You guys that have had a little more science? It means that the distance for y is, it's decreasing, right? It's decreasing at a rate of 3/4 feet per second. So while x is going out at a foot per second, the ladder is dropping at 3/4 foot per second at the exact instance when the ladder is 6 feet from the wall. What's going to happen as the top of the ladder gets closer to the ground? Is the rate that's going toward the ground going to speed up or slow down? Yeah, unfortunately for anybody at the top of the ladder, it's going to speed up. Yeah. Any questions on that problem? Okay, here's our next one. This is one for us to try here. It says if V is the volume of a cube with edge length x, and the cube expands as time passes, find dV over dt in terms of dx dt. So this is not asking us to find a numerical answer like we did on the other problems. This is just asking us to basically set it all the way up and solve for dV over dt. So if you're working offline here, go ahead and pause the video now, try the problem, and you're ready to check your answer with ours. Press play. All right, back at this. I think you guys were doing pretty well with this. All you got to do is realize, hey, I know how to find the volume of a cube. The edge length is x, so the volume is x cubed. And then if you differentiate both sides, you're pretty much there. The derivative of v with respect to t is dv over dt. The derivative of x cubed with respect to t is 3x squared times the derivative of x with respect to t, which is going to be dx over dt. That's what they asked us to do. Find dv over dt in terms of dx dt. We've done it. We can't go any farther. Yep. Try this one. Each side of a square is increasing at a rate of 6 centimeters per second. At what rate is the area of the square increasing when the area of the square is exactly 16 square centimeters? If you're working at home, now's a good time to pause when you're ready to check your answer with ours. Please press play. All right, let's take a look here. Are we given, if I let this side be x instead of s, so I don't think it's a 5 later in my calculation, is that okay? Okay, so dx dt is increasing at 6 centimeters per second. Agreed? What do we want to know?
We want to find dA over dt.
dA dt when?
The area is 16.
Can I say that differently? When x is 4. Or when a is 16. Same thing, right? We can state that either way. So it's just a square, so the area formula is pretty straightforward. Area equals x squared. We derive the left side, we get dA over dt. We derive the right side, we get 2x dx over dt. We know x over dt, right?
Yeah.
And we know x when the area is 16.
Yeah.
X when the area is 16 is going to be 4. So when a equals 16, the side is 4. That's what we're trying to find. So sometimes you have to take this statement, like when the area of the square is 16 squared, and you have to interpret that a different way. Like in the blue here, when the area is 16, the side length is 4. Because x is a side length, and we need to be able to substitute for that in the function. We don't need to be able to substitute for the area anywhere. We're actually trying to find dA dt at a specific time, or a specific point in that increase. That's all there is for us to learn today.